two statistics that can help us better understand how variables are associated with each other when we have more than one explanatory variable are the partial and semipartial correlation coefficients that we're going to look at in this video. Let's begin, however, by reviewing the simple or zero order correlation coefficient that you know. You originally learned about it as Pearson's correlation coefficient, and you know that it measures the association among two variables, such as one explanatory and one response variable, or just two variables regardless of whether you identify an explanatory and response variable. You know that the correlation coefficient can range from -1, a perfect negative correlation, to +1, a perfect positive correlation, and 0, meaning no correlation, but typically we get something between those values that I just mentioned. So I'm going to use the health data that I've used in a previous video, and let me go ahead and load that data. So let's begin by looking at the correlation for the number of doctors and hospital beds in small cities. You might remember that in a previous video, I wrote a report to see what variables we could use to predict the number of physicians that would be in a small city, perhaps indicating what variables small cities could focus on if they want to increase the number of physicians, if in fact it is a causal relationship, which we don't know for sure, but we start by exploring potential cause when we look at correlations. So here's the correlation for the number of doctors and hospital beds in small cities. It's about 0.30. You know that one of the easiest ways to interpret the correlation coefficient is to square it, because squaring the correlation coefficient to obtain what we call the coefficient of determination, that coefficient of determination tells us what proportion of the variation in the response variable, in this case physicians, can be associated with, or perhaps even explained by, variation in the explanatory variable, in this case the number of hospital beds. And the answer here is 0.09, or 9%. So about 9% of the variation in the number of physicians across these various small cities that we collected data on, or someone collected data on that we're using for this analysis, about 9% of the variation in the number of physicians can be accounted for by the number of hospital beds, that is, the variation in the number of hospital beds. If we want to look at a model in which we're actually predicting doctors from hospital beds, remember, to get a correlation, you don't actually have to have a model like this. You don't even have to indicate what's the explanatory and what's the response. But once we start doing model building, because we want to understand what causes changes in variation of one variable by looking at other variables, then we do construct a model. In this case, we've been constructing linear models. Thus, we're using LM, the R function for a linear model, and getting a summary of that. And you see that the multiple R squared we obtain up down here is 0.07874, the same as what we obtained up here. The only thing that makes this a multiple R squared is it can generalize to more than one explanatory variable. So when we're talking about a single explanatory variable, we talk about a small r squared. When we're talking about one or more explanatory variables, we can have a multiple r squared. It is a generalization of the small r squared for a single explanatory variable when we have more than one. Now in this case we only have one, and so we have that multiple r squared of 0.0874. Now what we have been doing in past videos is we've been looking at multiple linear regression, in which we look at the relationship of a number of explanatory variables to the response. In each one of these, we are assuming, or we have a belief that there's a linear relationship of the explanatory to the response variable, so we can put this all together in a linear model. So let's go ahead now and add income to the model as a first step towards understanding how there are different correlation coefficients we can use to better understand the role of each of the variables in our model. So here we're adding income to the model. And when we add income to the model, we end up now with a new multiple r squared of about 0.27. 0.27. So without income in the model, with only beds, we had 0.09. But now with income in the model, still keeping beds in the model, but now adding income, we see that we have quite an increase all the way from 0.09 to 0.27. So in essence, we had about a 0.18 or 18 percentage points increase in the amount of variation in the number of physicians that can be accounted for by our model. So what we're doing when we're looking at semi-partial and partial correlation coefficients is we're looking at two different ways to see how variables contribute to explaining variation of a response variable in the presence of other variables that are in the model. The amount of increase of the multiple r squared that we just obtained here, that amount of increase is the square of the semi-partial correlation. So even though we're learning about partial and semi-partial correlations, just like with simple correlations, it's easier to talk about the meaning of that variable when we square it, because now we can talk about proportion of variance accounted for. We can, of course, take the square root of that if we want to get the actual correlation coefficient, and these also range from -1 to 1. So I'll talk about that a little bit later. But first of all, let's start with just taking the square of the semi-partial. And the square of the semi-partial is just the increase in the proportion of variation in the response that you can obtain when you add a variable to the model. So here, the square of the semi-partial correlation, I'm doing it again down here by taking the r squared for my beds income model and subtracting only the beds model. And what we get when we do that is what I just did a moment ago that we all did in our minds, just thinking about going from 0.09 to 0.27. And that is we're seeing we had a change of 0.18 or 18 percentage points. So what is that? That is the square of the semi-partial correlation among income and physicians, okay, our new explanatory variable, income and physicians, when accounting for the variation that can be explained by the number of hospital beds. Now, what I show here is that the semi-partial correlation coefficient that we just obtained by taking the difference in the r squared of the two models is the same as removing the effect of beds on income and then correlating this residual with the response variable. And by squaring, we can get the squared semi-partial. Without squaring, it's just the semi-partial correlation. So what I'm doing here on line 51 is I am actually creating a model in which I regress income on beds. Why am I doing that? I'm trying to remove the effect of beds out of income. So when I take the residual of that model, as I do on line 52, I'm now looking at income without any effect of beds in it, and I am correlating that with doctors. And then on line 53, I'm taking the square of that correlation. So if we run that, Right away, my I drops down to that 0.18 that we've seen before. That is that we are now looking at 18% increase in the variation in physicians accounted for. When we add income to our model above and beyond hospital beds, that is, when we've already taken hospital beds into account. And so I did it two ways here. One is I created two models. That's what you see on line 45. I created two models and took the difference in the multiple R squared for the two models to see how much extra I got when I added income. And the second way I did it, that was equivalent, was to remove the effect of beds from income by regressing income on beds, and then take the residual from that and correlate it with doctors. So you can almost think of that residual as a residual that is bed-free, a residual of income after any correlation with beds has been removed. So if income and beds are correlated, well, we've got to take some of that and account for it with beds before we then can calculate the semi-partial correlation with physicians as we've done here. All right, so I kind of did this a little bit backwards because what I did to give you an overview of how semi-partials work is we went through some analysis in which I showed you how to calculate semi-partial. I think that's going to be helpful for understanding as I dig a little bit deeper into the meaning of the semi-partial. You already have some sense of the meaning. It's how much more can I add to my model when I add that variable? If the semi-partial's a lot, then that variable is probably going to be very important to my model. But let me show you in the next video some other things about semi-partials in terms of notation and in terms of understanding what they mean. So I'll see you there.